Here we're going to look at the relationships between segments and parts of a segment and the whole. And we're going to use this in the segment addition postulate to find unknown lengths. So talking about segment lengths, the length of a segment, also known as the distance between the endpoints, is represented using the capital letters representing each of the endpoints. You do not need the bar over it. So for example, the length of segment AB would just be AB without the bar. Now, if we're looking at distances on a segment, we want to think of, first of all, we're just only going to do collinear points. And in this example, we say Anthony is driving from LA, Los Angeles, to San Diego. He looks at his trip meter while passing through Anaheim and sees that he's already gone 24 miles. The sign says he still has to go 97 more miles to get to San Diego. How would you find the distance from Los Angeles to San Diego? Think about it. Well, I'm hoping that you would add these two parts to get the whole distance. So you would say 24 plus 97, which is 121 miles. Now, the segment addition postulate comes from that basic idea. If I have a segment A and B and C, so AC, and here's the two pieces, they have to add up to the whole. So here's the segment addition postulate. If A, B, and C are collinear, that means they share the same line, and B is between A and C, then AB plus BC is the same as the distance or the length of AC. Or as I said before, the sum of the parts adds up to the whole. To solve problems, what you're going to do is set up an equation where one side of the equation is the whole and the other side is the sum of the parts. It doesn't matter if you put the whole on the left or the right. The whole goes by itself on one side and the sum goes on the other. Okay, in this example, we're going to find the length of segment LN. There was a typo on your notes and it says LM as in Mary. It's LN as in Nancy. So the first thing we're going to do is we're looking for the whole. And we're going to start by adding the parts. So we have 17 and 3y. We're going to put those together and we should get 9y minus 7. So 9y minus 7 should equal 17 plus 3y. It does not matter if you have this on the left or the right, just as long as they're both there and there's an equal sign between them. Our justification, our reason that we can write this, is because of the segment addition postulate. So you might want to start remembering some of the names of the more popular postulates. This is a good one. And that's a justification for setting up an equation. Now, I really want to solve for y, because if I'm going to find ln, you can see it's related to how big y is. So first of all, I need to isolate y, get it by itself. I have more y's over here, less over here, so I'm going to take minus 3y from both sides, which gives me 6y minus 7 equals 17. Why am I able to do that? Well, I'm allowed to subtract the same thing from both sides of an equation. That's called the subtraction property of equality. Then I want to get rid of this minus 7, and the way I undo that is by adding 7 to both sides. So I'm going to get 6y equals 24 from the addition property of equality. Then I can solve this by dividing both sides by the same number. I'm dividing them both by 6. Why? Well, that's kind of almost a joke. I'm dividing 6y by 6 because I'm trying to get to 1y. So dividing both sides by 6, I get y is 4. And the reason I'm allowed to divide both sides by 6, that's the division property of equality. So finally I pull out ln equals 9y minus 7. Well, where did I get that from? I got it from the problem, so I can say that's actually given to me. Then I'm going to substitute in the 4 in for the y. 9 times 4 minus 7. And yes, that comes from the substitution property of equality. And finally, I just go ahead and do some multiplication and subtraction, and I get 29 is the length of ln. So what is the difference between CD without a bar and CD with a bar? Those are two different things. And how do you know how to set up an equation for the segment addition postulate?